Imagine for a second trying to find a single microscopic working assembly line hidden deep inside this massive, otherwise completely abandoned factory.
It's a daunting visual, yeah.
Right. Like you can't just blindly poke around in the dark hoping to strike gold. You have to know, well, exactly how the factory was built, how the machines are supposed to work, and, where the very last remnants of power might be hiding out.
Which is exactly why structure is so important.
Exactly. And if you're joining us for this deep dive today, that is the exact architectural puzzle we are trying to solve with you. We're looking at the male reproductive system, but we're really slowing things down today.
We are taking a very deliberate look.
Yeah, a highly focused look at this microscopic landscape. Our mission here is to understand how a single stem cell transforms into a mature sperm cell. And crucially, how understanding that exact biological geography, dictates the surgical strategies doctors have to use when the entire system just fails to produce.
It really is a phenomenal architectural journey. And to piece this all together for you, we're pulling from a pretty serious stack of comprehensive sources.
Oh, yeah. Heavy reading this time.
Definitely. We've got major medical textbooks on assisted reproduction, the latest clinical guidelines on male infertility from the World Health Organization, and some really incredible molecular research detailing both the cellular journey of spermatogenesis and the modern assisted reproductive technologies we use today.
And I think it's important to state up front because, solving male infertility is often mistakenly thought of as just this, simple hormone balancing act.
Right, the old just give them some testosterone myth.
Yeah, like you just prescribe a patch or a gel and you're good to go. But it isn't. It is fundamentally an exercise in structural geography. Knowing exactly where to look for sperm is entirely dependent on understanding, how and where it is physically made.
Precisely.
So before we can even begin to understand how a surgeon retrieves a missing product, we really have to tour the factory where it's built.
We do. And understand the testis, you have to realize it's essentially divided into two distinct, highly specialized functional compartments.
Okay.
You can picture them as the internal factory floor and then the external neighborhood that sort of surrounds it.
Let's start on that factory floor then. Structurally, we are talking about the seminiferous tubules.
That's right.
Because our sources note there are about 500 of these tightly coiled tubes packed into each testes, which makes up a massive 80% of the actual testicular volume.
It's a huge proportion.
Yeah, the stat that blew my mind was if you unspooled them, they would stretch for hundreds of meters.
Yeah.
Just inside the body.
It's incredible packaging.
And they're lined with these fascinating structures called Sertoli cells, which the literature literally calls the nurse cells.
Because that's exactly what they do.
So,
They physically cradle the developing sperm, providing metabolic substrates, like lactate, for energy.
but they also physically lock together, right? Like tightly weaving their membranes to create this highly restrictive border called the blood-testis barrier.
Yes. Meanwhile, right outside those coiled tubules is the interstitial compartment. This is what we call the neighborhood.
Okay, the neighborhood.
Right. It's where the blood vessels, the lymphatics, and crucially, the Leydig cells live.
The Leydig cells?
Yeah, those Leydig cells are essentially the power generators for the whole operation. They're responsible for producing massive amounts of testosterone in response to luteinizing hormone, which comes from the pituitary gland.
And when we say massive, the sources were very clear on this. The localized intratesticular testosterone concentration is up to 100 times higher than the circulating levels you would find in the rest of your bloodstream.
It's a staggering difference, yeah.
And that overwhelming local concentration is an absolute non-negotiable requirement for sperm production to even occur inside those tubules.
Exactly. Without that local power grid, the factory shuts down entirely.
Okay, let's unpack this setup because it's honestly wild to me. We basically have a highly secure clean room assembly line, the seminiferous tubules, which is being powered by this intense external generator of Leydig cells out in the neighborhood.
That's a great way to visualize it.
But I have to push back a bit on the security system, or at least ask about it. Why is it so strictly necessary to have a blood testis barrier? Why does this clean room need to be walled off so aggressively from the rest of the body's circulation?
That is the big question.
Okay.
And that barrier serves two absolutely critical life-preserving functions. The first one really comes down to immune privilege.
Immune privilege. Okay.
Think about the timeline of human development. Spermatozoa are not produced until puberty, right?
Right.
Which is long, long after the body's immune system has already fully matured and cataloged every single protein in the body as self.
Oh, Oh, wow. I never thought about the timeline like that.
Yeah, so because sperm are essentially new creations with totally unique genetic material, their surface antigens are entirely foreign to your immune system.
Wait, really?
Yes. If those sperm antigens were to just casually enter the systemic bloodstream, your own white blood cells would instantly recognize them as alien invaders.
So the body would attack its own reproductive cells.
Exactly. The body would mount a massive attack, creating anti-sperm antibodies that would severely and often permanently destroy natural fertility.
So without that physical wall locking them away, your body treats them like a virus.
It treats them exactly like a virus. It's fascinating. And then the second reason for the barrier is biochemical.
Okay.
The blood-testis barrier creates a perfectly controlled microenvironment. Spermatogenesis requires a very specific, shifting gradient of nutrients, hormones, and signaling molecules.
So it's highly sensitive.
Incredibly sensitive. That delicate balance simply cannot be maintained if the tubular fluid is constantly mixing with the chaotic, fluctuating general bloodstream.
Right, it would just wash all those precise signals away.
Exactly. The barrier allows the different highly sensitive stages of cell division to proceed in a protected, tightly regulated space.
Okay, so now that we have a really clear picture of this protected clean room, let's actually track the assembly line itself. For humans, it is a 64 to 70-day physical journey for a developing cell, which is longer than I would have guessed.
It takes time to build something that complex. And I should warn you, the naming conventions our sources use here are strict, and they're highly specific.
Yeah, it gets a bit dense.
They might sound overly technical at first, but each name denotes a completely different biological and structural reality. We have to use them.
Let's walk through them then, because this is where the how gets really fascinating. The journey begins at the very base of the tubule, right against the basement membrane, with the spermatogonia.
Right, the stem cells.
These are the stem cells. The literature breaks them down into AD, AP, and B classifications, which sounds like alphabet soup until you realize what they actually do.
The classifications tell us exactly how the factory sustains itself over a lifetime. So AD stands for adark, named for how they look under a microscope. These are the deep, silent reserve cells. They rarely divide. They just wait, ensuring the factory literally never runs out of raw material.
An ultimate backup system.
Exactly. Then you have the AP, or apale cells. These are the active progenitors. They're constantly undergoing standard cell division mitosis to multiply and proliferate.
Just pumping out numbers.
Right. And eventually, they transition into B spermatogonia, which are the cells preparing to take the massive leap deeper into the tubule.
And that leap is a big one. These B cells have to actually cross that blood-testis barrier we just talked about, physically moving away from the basement membrane and pushing toward the center of the tubule.
Yes.
And when they cross, the name changes. They become C1 cells.
C1 being the primary spermatocytes.
Exactly. Primary spermatocytes are the C1s. At this C1 stage, something incredible happens. They enter meiosis side. This isn't just, copying and pasting DNA.
No, this is much more complex.
This is where homologous recombination occurs. It is a literal genetic shuffling, physically crossing over pieces of DNA so that every single resulting sperm will be entirely genetically unique.
It's the engine of human diversity happening right there.
Yeah.
And once that intense genetic shuffle is complete, they divide into C2 cells, which are known as secondary spermatocytes.
C2 cells.
Okay, now the C2 cells have a very brief lifespan because they rapidly execute meiosis II, splitting their genetic material again. And that specific division brings us to the round spermatid stage.
Let's pause on the round spermatid because structurally this is a massive milestone. These round spermatids are the very first cells in this entire sequence that have a haploid set of chromosomes.
Yes, exactly half.
Meaning they finally have half the genetic material, the exact correct 23 chromosomes, ready to pair with an egg. But I read a detail in the sources that totally threw me off.
What was that?
Even though they are individual cells now, they don't fully separate. They stay physically connected to each other, sharing cytoplasm through these tiny little bridges.
They do, and the reason is brilliant. Because they are now haploid, some cells might have an X chromosome and some might have a Y.
Oh, right.
So they carry different genetic codes, meaning they produce different essential proteins. By staying tethered together via those cytoplasmic bridges, they can share those gene products back and forth.
Oh, wow. So they're keeping each other alive.
Exactly. It ensures the entire developing cohort survives together. But, as you noted, they are around. They're haploid, yes, but they are completely non-functional as a reproductive vehicle at this point.
Right, and this was my big question reading through this. If a round spermatid has the exact correct amount of DNA for a human being, why can't it just do its job?
It's a fair question.
Like, why does a body expend so much intense metabolic energy going through this next phase, which the literature calls spermiogenesis, to become an elongated spermatid and then finally a full sperm?
Well, if we look at the logistics of human reproduction, having the correct DNA is only 10% of the battle.
Only 10%.
Yeah. The round cell has the blueprint, sure, but it has absolutely no delivery mechanism. Spermiogenesis is a dramatic, violently physical overhaul of the cell.
Violently physical. I like that.
It really is. The nucleus shifts all the way to the periphery. A flagellum, the tail, begins to protrude, and that is non-negotiable for transport through the immense distance of the female reproductive tract.
Without the tail, they're going nowhere.
Right, and an acrosome forms, like a specialized cap over the head of the cell, packed with highly corrosive enzymes. Those are required to physically burn through the egg's tough outer shell.
And as it elongates to do all this, it just throws away almost all of its cellular machinery. Huge amounts of unnecessary cytoplasm are just shed entirely.
You have to travel light.
Yeah. And those nurse cells, the Sertoli cells, they literally act as a cleanup crew, phagocytosing or eating all that discarded baggage so it doesn't clog up the tubule.
But the most important structural change during this elongation phase happens deep inside the nucleus. The structural packaging of the DNA changes completely.
Oh, the histones.
Yes. Normal cellular proteins, called histones, act like loose spools the DNA wraps around so the cell can easily read its genes. Just everyday cell function. Right. But during spermiogenesis, those histones are violently stripped away and replaced by specialized, much smaller proteins called protamines.
I love how the sources describe this part, because protamines pack the DNA incredibly densely. They essentially shut down gene expression entirely and physically armor the fragile genetic code for this treacherous journey.
It's a total lockdown.
It really is. It's like taking a sprawling architectural blueprint that was spread out all over a desk, folding it up as tight as possible, and locking it inside a titanium briefcase.
That titanium briefcase is a perfect analogy. And once the blueprint is locked away, they finally become mature spermatozoa, the full sperm, and are released from the Sertoli cells into the empty lumen, which is the center channel of the tubule.
So a factory floor has built the product. It has its tail, it has its dense protamine briefcase, and it's washed out of the testes.
Journey complete, right?
Well, no, that's the wild twist. These full sperm that leave the testes are actually totally immature. They can't even swim yet. They have to go to what the clinical literature essentially describes as a finishing school.
The epididymis.
Yes, the epididymis.
It is a tightly coiled, highly specialized tube sitting right on the back of the testes. Structurally, it's divided into three sections: the head, the body, and the tail, or the caput, corpus, and cauda.
And they're not rushing through it.
No, sperm are slowly pushed through this structure over the course of anywhere from 1 to 12 days.
And a tremendous amount of maturation happens during that transit. For one, 90% of the fluid that carried them out of the testes is reabsorbed.
Concentrating the sperm.
Exactly. But more importantly, this is where they acquire forward motility. The factory built the tail, but the epididymis is where they actually learn how to turn the engine on and swim straight.
It's the testing ground.
Right. They also undergo crucial biochemical modifications to their surface proteins, prepping them for the eventual precise moment they make contact with an egg.
And expanding on your titanium briefcase analogy, the epididymis is where the physical locks are finally put on that briefcase.
The disulfide bonds.
Yes. Inside the epididymal environment, strong disulfide bonds are formed. Aided by very specific reactive oxygen species, these bonds cross-link and stabilize those tiny protamine proteins we discussed earlier.
So it's reinforcing the structure.
It literally weaves a layer of chemical armor, protecting the tightly packed DNA from fragmentation.
I really want to emphasize that point for everyone listening. It's like the testes is a car factory. It builds a vehicle that looks exactly like a car. It has an engine. It has wheels. But the epididymis is where they finally put gas in the tank, run the diagnostic tests, and reinforce the chassis with steel.
That's a great way to put it.
So if the epididymis is where the DNA gets armored with those disulfide bonds, does that imply that raw testicular sperm, like the ones that haven't gone to finishing school yet, are actually incredibly fragile compared to ejaculated sperm?
They're immensely fragile. Because they lack that final disulfide cross-linking, testicular sperm are highly susceptible to DNA damage the second they are removed from the body.
Wow.
And that biochemical reality sets the entire stage for clinical interventions. The specific anatomical source of the sperm completely dictates how resilient that sperm will be in the IVF laboratory.
Which brings us to the real clinical stakes of this deep dive. When the system breaks down and a patient presents with azoospermia.
The clinical term for having absolute zero sperm in the ejaculate.
Right, zero sperm. When that happens, doctors don't just guess. They use the exact geography we just mapped out, the factory of the testes versus the road of the epididymis, to determine their surgical strategy.
That's a structural roadmap.
Yeah. The sources divide this failure into two completely distinct biological realities: obstructive azoospermia, or OA, and non-obstructive azoospermia, or NOA.
And the distinction between the two changes the entire surgical playbook. In obstructive azoospermia A, the factory is working perfectly.
So it's still making sperm.
Yes. Spermatogenesis, from spermatogonia to C1 to C2 all the way to full sperm, is happening normally. But the road out is blocked.
Ah, okay.
The causes here are usually physical barriers. It might be a congenital absence of the vas deferens, which is frequently linked to genetic mutations for cystic fibrosis, actually.
Oh, interesting.
Or it could be a previous vasectomy or severe scarring from a post-infectious disease.
So the product is pristine. It just hit a roadblock.
Exactly.
But then we have non-obstructive azoospermia, NOA. In this scenario, the road is perfectly clear, but the factory itself is failing. The assembly line is just shut down.
It's a much harder problem to solve.
Right. Maybe the cells undergo maturation arrest, where they just abruptly stop dividing at the C1 or C2 stage. Or maybe it's Sertoli cell-only syndrome, where the entire tubule is just empty nurse cells with absolutely zero stem cells.
Just a barren factory.
Yeah, and our sources note that NOA actually makes up a massive 2/3 of all azoospermia cases.
Which highlights why a thorough clinical evaluation is paramount. A physician must determine definitively if they are dealing with a plumbing problem or a deep-seated production problem.
So for you listening, picture the fundamental difference in the doctor's objective here. In OA, the surgeon's job is just to bypass a roadblock to retrieve fully mature, robust cells. But in NOA, the surgeon has to physically dig into a failing, collapsing factory, desperately hoping to find a few rare, isolated scraps of active production.
That's the challenge.
Because these biological realities are so distinct, the specific surgical tools and target locations are completely different.
Let us examine obstructive azoospermia first. Because the factory works, the surgeon's primary target is the epididymis.
They want the armored sperm.
Precisely. They utilize techniques like PISA, which stands for percutaneous epididymal sperm aspiration, and that just uses a needle through the skin.
Yep.
Or they might use MESA, which is a highly precise microsurgical aspiration.
But the goal is the same.
Yes, the goal is to extract sperm directly from the epididymis, because those sperm have gone through finishing school, they have motility, their DNA is armored with disulfide bonds, and they are highly fertile.
But what if that epididymal retrieval fails? Say the epididymis is too heavily scarred from an infection to yield anything. The surgeon has a fallback, right?
They do, and it is a highly reliable one for obstructive cases. They can perform a TESA, which stands for testicular sperm aspiration.
TESA.
It is a relatively simple blind needle aspiration directly into the tissue of the testis. And in obstructive cases, it has a near 100% success rate.
Even though it hasn't gone through the finishing school.
Yes, because the testis is absolutely overflowing with healthy, fully formed spermatozoa just waiting to get out.
Okay, so a simple needle poke works wonders for OA. But for non-obstructive azoospermia, the strategy has to shift dramatically.
You can't target the epididymis.
Right, because it's going to be completely empty. The surgeon has to bypass the finishing school entirely and go straight to the factory floor, the testes. But a blind needle poke, a standard TESA, usually fails miserably in NOA cases.
It does? Why?
Because production in a failing testes isn't uniformly diminished. It's extremely patchy.
Exactly. Sticking a needle in blindly will likely just aspirate empty scar tissue. Therefore, the gold standard for NOA is a procedure called micro-TEES, or microsurgical testicular sperm extraction.
Micro-TEES.
Yes. The surgeon actually opens the testes, utilizes high-powered optical magnification, and physically hunts through the tissue for specific, visually distinct seminiferous tubules that might still be managing to produce sperm.
I have to pause on the actual mechanics of this surgery. If a patient's entire factory is failing, like if their hormones are completely off, or the genetics are causing widespread maturation arrest. How does looking through a microscope actually help the surgeon?
It's a good question.
What are they physically looking for in there that a needle couldn't just stumble upon?
It comes down to scale and visual pathology. In a failing testis, the vast majority of the seminiferous tubules completely collapse. They become these flat, fibrotic, yellowed strings of scar tissue.
Just totally dead.
Right. But spermatogenesis can be incredibly focal. So during a microtease, the surgeon is hunting visually for rare, plump, opaque tubules.
Plump tubule.
Yes, an opaque, slightly swollen tubule indicates that there is fluid and cellular volume inside. It suggests that in that one specific microscopic neighborhood, the Sertoli cells are still functioning, the blood-testis barrier is intact, and an active assembly line might still be running.
Wow.
The surgeon is meticulously picking out the one active machine from a sea of abandoned, collapsed machinery.
That is a staggering visual, finding the one plump tubule among thousands of flat ones. And, if they open that plump tubule and still can't find full sperm, there are experimental fallbacks we should probably mention.
Yes, clinics can attempt RSI or ELSI.
Round spermatid injection or elongated spermatid injection.
Exactly. They essentially extract those immature cells we talked about earlier, the ones that have just finished the C2 division, but haven't fully shed their cytoplasm or packed their DNA.
Right.
But the success rates drop incredibly low because you are forcing a raw, highly immature cell to do the job of a fully armored sperm.
Which really brings us back to the importance of the sequence.
Mm-hmm.
Those cells in ROSI and ELSI entirely lack both the dramatic nuclear overhaul of spermiogenesis and that crucial epididymal maturation process.
They miss the armor.
Yeah, they miss the armor. So, to bring this all together for you listening, we've tracked an incredible architectural journey today.
We really have.
We started with a single stem cell on a basement membrane. We watched it cross the highly secure blood-testis barrier to become a C1 primary spermatocyte, shuffling its genetics. We saw it divide into a C2 secondary spermatocyte and then transition into a haploid round spermatid.
It's a long road.
It is. We marveled at how it shed its physical baggage to transform into an elongated spermatid, locking its DNA in that titanium protamine briefcase. Finally, we watched it gain its chemical armor in the epididymal finishing school.
And all of that dictates the clinic.
Exactly. We've seen that whether a surgeon uses a simple needle for PISA or a high-powered microscope to hunt through a dying factory in a microtease, the strategy is entirely dictated by knowing exactly where that sequence broke down.
Synthesizing all of this actually raises a profound question that the field of reproductive medicine is actively grappling with today.
Oh yeah, this is the big one.
We have clearly established that the epididymis is a crucial checkpoint, right? It is the finishing school that locks down the DNA with desulfide bonds, and it naturally weeds out defective cells.
Right.
By relying heavily on techniques like microtease to extract raw, fragile testicular sperm for in vitro fertilization, bypassing that natural finishing school and quality control checkpoint entirely. Are we fundamentally bypassing an essential step of human evolution?
That is such a heavy thought.
It is. And if we are, what might be the long-term epigenetic consequences for the offspring conceived without that crucial epididymal armor?
That is exactly the kind of question that keeps you up at night. We are fundamentally altering a biological sequence that has been refined over millions of years, and, we are really only just beginning to understand the long-term echoes of that intervention.
We are at the very beginning of understanding it.
But the main takeaway here for today, structure always dictates strategy. On our next deep dive, we are going to flip the script entirely and explore the female reproductive tract.
It's going to be a great discussion.
Oh, absolutely. We'll see how female anatomy doesn't just produce gametes, but is structurally engineered to receive, host, and intricately nourish a developing embryo. It's a biological system forced to do two massive, often contradictory jobs at exactly the same time. You definitely won't want to miss it.